Welcome back. We're going to talk about spanning tree concepts and per-VLAN spanning tree, which is a Cisco technology that's proprietary to their switches. So what is spanning tree and why do we need it? So we want redundancy in our enterprise networks, right? Redundancy is going to be a very, very important topic throughout your CCNA studies. Redundancy, redundancy, redundancy. And I know I sound repetitiously redundant when I say that, but it's really, really important. Like I usually tell people when we're going to purchase things and they go, why do you need two of whatever it is? Then I go, well, two is one and one is none. Really, you need to have two because if you don't have two and one fails, well, you're sorry. Sorry, you're out of luck. That's it. So we want to have two of everything. Now, some equipment we have spares of that maybe we can just have one on the shelf. However, usually when we're talking about stuff like firewalls, core switches, we really want to make sure we have two of those. Access layer switches, we usually just have one on the shelf, keep a spare, and of course keep our support up to date so we can get RMAs if we have a hardware failure. So redundancy is really, really great. We want to have redundant paths, right? So if we have maybe a switch topology like this, we can have two different paths. If we have a user over here, he can either go up to this switch or through this switch. So if we have maybe this link fail, we have a backup. Now the problem is redundancy can cause loops at layer 2. And so the way that we deal with that is we use this technology called spanning tree. Plugging a switch into itself can also cause loops, right? So maybe we have a user, and I've literally heard stories of this. You have a wall port in the wall here, and you've got, maybe 4 ports, and something's wrong with their computer. It's plugged in here, and there's just a cord dangling here. They go, oh, must not be plugged into the wall. So they unknowingly, maybe there's a piece of furniture here or something, go and plug it back in over here. Well, now you've got a loop, right? So the connection will come through this port and back out that port and back into your switch. This can also create a loop. We want to prevent these loops. And really, we're talking about layer 2 loops. When we talk about loops here, there's different ways to remediate loops at layer 3. And of course, we will talk about that in the respective video. So some vocabulary when we're talking about spanning tree. The root bridge is the switch to become king. So the root bridge really makes the decision, not necessarily makes the decision, but the root bridge is where all of our switches want to go. So for example, we have our 3-switch network here. If this guy is the root bridge, abbreviated RB, then in one way or another, this link is going to get blocked because our quickest path to the root bridge is these ways respectively from each switch. So we really want to be able to get to the root bridge the quickest, and that's how we calculate which links we're going to disable when it comes to spanning tree. The root port is going to be the port on the switch that's closest to the root. So in this case, this port and this port. Now, if we added a switch over here, our root port would be over here. Now, keep in mind, your root port wouldn't be on this side. It would be only one root port per switch. And we'll go into detail about this stuff in a moment. We have the designated port. So the designated port are going to be all the ports on the root bridge and any other active port other than our root ports. So all of our ports on our root bridge are designated because all those ports are the closest to the root. We're not going to disable any of those ports. Any other active port on other switches besides the root port is going to be a designated port. So in this diagram here, let me change my color so it's easy to see. Change to pink here. So this would be a designated port. This would be a designated port. This would be a designated port. Any other ports here connected to any other switch maybe would also be designated ports. Or maybe an end device as well. Then we have our cost. So this is going to be the value associated with link speeds to determine the best path to the root, right? So we're going to do a combination of link speeds and how many links, right? We add those together to get the total cost to the root bridge, and that's how we decide whether or not which link to select. We also have blocked or alternate ports, depending on what version of spanning tree you're running. Any non-root or designated port, these are going to be deactivated in some form or fashion. Either going to be blocked or they're going to be alternate, which is kind of like a what's the word to say? Kind of a hurry up and wait kind of situation. So they're ready, they're prepared, they're just kind of waiting to become active there. A little bit faster, and we'll talk about that when we get there. So the spanning tree algorithm itself was actually published in 1985. And you might be looking at that and thinking, that's ancient technology. 1985 was forever ago. How is this relevant today? Well, there's a few reasons. One, it was very well developed. Two, it's been adapted since then to suit our new needs. And really, it's stood the test of time very, very well. And if you look at some, it depends on your situation. So if you have a layer 3 campus design, the value of spanning tree is really diminished. However, if you have a layer 2 campus design, you're going to heavily rely on spanning tree. So it depends on, your architecture for your network. Now, a lot of big data centers, a lot of these massive companies, they're going to use layer 3 campus designs. For a lot of the smaller companies, a layer 2 campus design is much more simple and will provide adequate switching for their needs. So really, we can summarize the algorithm with these 3 ideas. We want to block redundant paths. All of this is going to be done automatically. So we're going to automatically block redundant paths. We're going to automatically create a loop-free topology. And we're going to automatically recalculate if a link failure occurs. Now this is great because we can provide some level of redundancy without having to do anything as a network administrator. It's all done automatically. There's going to be several steps that are going to happen when we use spanning tree. So first we're going to do our election. So we're going to elect the root bridge based on the lowest bridge ID, which is a bridge priority plus the extended system ID if you're using PVST plus the MAC address. So the bridge priority is manually set by us. We can go and set the bridge priority manually. Now, the extended system ID is just for PVST/PVST plus. Now, keep in mind that this is a Cisco only technology, so it's only going to be relevant in Cisco switches. But that extended system ID is going to give us the difference between which VLANs it is. So we're going to be able to know what VLAN it's in based on that extended system ID. And then the MAC address is a tiebreaker if everything else is the same. So that way we have some kind of tiebreaker. MAC addresses are unique to every switch. Therefore, there will never be 2 identical MAC addresses. There will always be a tiebreaker. Now, our bridge priority in PVST is going to be in increments of 4096, and that is because we need 4096 options for our VLANs. So that's where our extended system ID comes into play, right? Usually when we're talking about Cisco devices, we're going to deal with the bridge priorities in increments of 4096. So you'll have stuff like 4096, 8192, etc., etc. Bridge priority is usually manually set. I mentioned that. Once we elect our root bridge, we're going to elect our root ports. So we're going to find the lowest cost to the root. And then if that is the same, then the lowest bridge ID of the next switch, then the port ID or port priority. So in this situation, we have the lowest cost to the root, it's always first. Now, if we have an equal cost to the root, maybe we have 2 different switches we can get to get to the root. Maybe we have I should draw instead of just talking. Maybe we have a topology like this, right? So that switch to bottom is looking, well, this and this cost are maybe the same. So he can go, okay, the lowest bridge ID of the next switch. Now, what if you have a situation where you have a situation like this? I plugged in 2 ports to the same switch, so he's got the lowest bridge ID on both of those ports. It's got the same one. We can manually set a port priority, or we can find the lowest port ID by default if we don't set a port priority on our ports, if we're connected to the same switch going forward. After we elect our root ports, right, we've elected our root bridge, we've elected our root ports. Now we're going to elect our designated ports. So any root any ports on a root bridge are going to be designated ports. Every single one, all the time, 100% of the time, every single one's a designated port. Bam. Super easy. All of our segments will have one designated port. Now you say, I'm not really familiar with the word segments. What do you mean segments? So when I say segments, let's use our 3-switch diagram here. We've got a segment here, we've got a segment here, we've got a segment here. So each link, think of the cable, the entire length of the cable, we're gonna have one designated port per cable, really. And so if let me redraw my diagram here. If I have some nice large switches, and I will draw, so this is our root bridge for this example. So this would be a designated port, right? Every port in a root bridge is designated. Our closest port to the root would be our root port. And just for the sake of this example, I'm just going to grab a random port as the root port. Now, keep in mind that all segments will have one designated port. Therefore, if this segment has a root port on this port, it will be designated on the other side. Very, very simple, very easy to quickly populate with very little information, a chart like this. So now we're going to look at this and we're going to say, okay, we have this issue. Everything else is going to be blocked or marked as alternate. So depending on our version of spanning tree, we'll either block or put as alternate this link. Now, only one side of it will become alternate because, again, we need to have one designated port on every segment. So that means one of these ports is going to be designated. And just for the sake of not going into deep discussion right now, this port will be simply because he is closer to the root than this port would be. And one of the things I want you to remember is lower numbers are always going to win when we're talking about spanning tree. So in a lot of layer 3 technologies like routing, higher numbers are better. However, in spanning tree's case, lower numbers, a lot of layer 2 technologies, lower numbers are going to be better, right? So lower costs are going to be better, lower priorities are going to be better. Every metric, every number is going to be preferred lower when we're talking about spanning tree. So here are some rules of spanning tree. We're going to put the closest port to the root bridge is the root port, right? Talked about that. Remember that one port is always a designated port on each segment. So one side is always designated. Doesn't matter if the other side is root, blocked, whatever. One is going to be designated. And everything else is going to be blocked because everything else creates a loop. So now I have this nice pretty diagram I could use here, and I'll demonstrate again. So if this is our root bridge, then all these would be designated ports. These would be root ports, and one of these would be designated and one of them would be blocked. Now in this case, we would have to resort on this link to bridge ID because our cost to the root bridge is the same. So maybe we have a little more complicated situation here. So let's say this is our root bridge. So all of these ports would be designated, right? Okay, put that for this little link here. And this would be our root port because going this direction would be longer. Let's just assume these are all the same speed. From this switch's perspective here, it's going to be a little complicated. We can know that this is not going to be the root port. This is not going to be the root port. But which one of these? Depending. So let's give them some port numbers, and let's assume the port numbers over here are the same. So 01 and 02, which one is preferred? Assuming we didn't set any particular configuration on these ports, hopefully you answered 1 because lower numbers are better in spanning tree. And so we would actually block this lower link here. This would become our root port, excuse me, our root port. And this would, now we would fight over the bridge ID of these two. Let's say this bridge ID is lower. Just give them some numerical values. So 2, this could have a BID of 1. This could have a BID of 4, BID 8, BID 9, BID 10, 11, 12. So now we're going to block this side because the bridge ID is higher, and this will become a designated port. In this case, our root port would be over here. That's our quickest way to the root bridge. So somebody on this link will be disabled in one way or another. So because we have a higher bridge ID here, we're going to disable this side, and this side will become a designated port. Now let's keep going down. So in this switch's case, we could have a link over here to this switch and then the root bridge, or we can have a link to this switch and the root bridge. Either way has the same cost. So we're going to look at what's next, the upstream switch bridge ID. So then we'll check and we'll see, hey, the bridge ID here is shorter. So we're going to pick this for the root port. And then of course you have a closer route to the root, so it become designated on this side and blocked over here. Now let's look from this switch's perspective, right? Same situation. This has a lower bridge ID, so we'll have the root port go this way. This one become the designated port. And so you'll see as we go, same situation, right? Root port here, disabled, designated, and designated. And so from all this, you'll see, right, these are all root ports on the other side, so they will be all designated here. We filled out this pretty quick. So what you'll see kind of as a common thread here is, one, we're pretty much not using this switch at the distribution layer very much. We've got it ready, right? All its ports are in designated mode, so it's prepared to receive traffic, but it's not actually receiving traffic, right? So this switch here is going to be bombarded with, 99% of our access layer traffic at least. Maybe we're using distribution layer switches in other ways, but if we're not, if this is the only purpose, then really it's more of a backup and it's being wasted. This is one of the reasons we have per-VLAN spanning tree, so that in our other VLAN, we can have the opposite. We can have the root bridge over here, and that root bridge, let's just say for the blue VLAN, this could be the root bridge. Okay, in the blue VLAN, this has a BID of 1, this one has a 2, etc. And so all the flow of the blue VLAN goes up to this switch, to this guy, and all the flow of the pink VLAN goes over to this guy and to this guy. So hopefully that makes sense. So what problems do we have that spanning tree addresses? So we have layer 2 loops, right? We talked about that. And really when layer 2 loops happen, we get these broadcast storms. So when we have a broadcast storm, that's going to be traffic that's just going to go in a circle over and over and over, right? Our broadcasts go to every port except the port it came from. And so it will be spit out all the ports, and then it will go to the next switch, spit out all the ports. And if there's a loop, it'll just keep going and keep spitting out all the ports until our switches get totally overloaded. Our link lights look like Christmas trees, and we're in a really, really bad spot. Now also it addresses link failures, right? So if we have, again, that little three switch network here, and we have spanning tree set up, then this link is blocked until this goes down, boom, explosion, catches on fire or something, That's dead, so now we can switch over and go this way. So I will demonstrate a broadcast storm. Say, for instance, spanning tree is disabled in this network. Now we send a broadcast to look for the MAC address of a device. It goes up this way and then this way because, again, a broadcast goes at all the ports that it did not receive it from. So then this switch is going to then broadcast it here. And I should really, let me start over here with the arrows. So the first arrows are going to be in blue, and then this switch is going to get it, and it's going to send it this way. And then our other switch here, we'll use yellow, is going to send it out. No, not that way. You undo that. Oh, my apologies. My apologies. It'll send it this way. And then also to the AP, and that will send it to this guy. Right? And then following our trend, right, the pink will get received to this switch, and this switch will send the pink here and here. And then this switch will receive the yellow and get back down here. And now this yellow packet will be received by this switch and go back to this guy and over here to this guy. And the pink packet will be also received and sent to this, oh, wrong color. Pink guy will be sent to this and up to this guy. So as you see here, like, we start to get in this big mess of everything's everywhere, and quickly our switches will become unresponsive and we'll have a really, really bad day. Now, of course, if we have a link failure situation, right, this link fails, we have a backup route. Pretty simple there. So when we're talking about electing the root bridge, let's go to it in detail here. Our switch, every time our switch is going to start up, they're going to declare that they are the king. I woke up, it's early in the morning. Good morning, I am the king. So every single switch when it boots up declares, I am the root bridge, challenge me if you dare. And then they send out a message every 2 seconds called BPDUs. Now these bridge protocol data units declare their kingship. They say, I am the root bridge, and all of you should bow down to me. And make sure your links go to me the quickest, and you should use me as your source of truth. These BPDUs also contain information like their bridge ID and the root ID, which they assume is themselves. So, and in this case, it is for them, but is it going to end up that way? We don't know yet. So this is who really they believe the root bridge is, right? The root ID. Well, then the bridge IDs are calculated with our bridge priority, our MAC address, and if we have PVST or PVST plus, we can have the system extended system ID to specify which VLAN. The default for Cisco devices is 32768. So you'll see that if we add the VLAN 1 extended system ID, then it will become 32769. So if you see in the interface 32769 instead of the 32768 you're expecting, then it's probably because they added VLAN 1 in PVST. Now, root ports are going to be determined by the lowest cost path to the root bridge. To determine the cost of the path, we're going to add up the values of the links, right? So the values for the links are gigabit is going to be a value of 4, 100 megabit is going to be a value of 19. And if the costs are the same, the bridge ID will determine the root port. If the bridge IDs match, so if it's the same switch, then the lowest port priority. Now, if those match, which they do by default, the lowest port number is used, right? Keep in mind that all of these are lowest. Everything in spanning tree is going to be the lowest is the priority, preference, whatever you want to say. So if there are no root ports on a segment, the ports with the highest bridge ID will become the designated port, and the other side will set to blocking or alt, again, depending on what kind of spanning tree you're using. So some of our timers, we're going to have a hello timer, which is in between sending BPDUs. The default is 2 seconds. Now we can set it to either anywhere between 1 and 10 seconds. The default being 2 seconds, I find just fine in most situations. Our forward delay timer is going to be the time spent listening and learning. The default is 15 seconds, and it can be set anywhere from 4 to 30 seconds. And then we have our max age timer. Now this is the maximum amount the switch waits before changing the spanning tree topology, also known as the spanning tree. The default is 20 seconds, and it can be anywhere from 60 to 40 seconds. Default times can be changed on the root bridge for the whole spanning tree domain. So the root bridge will basically communicate these times to the rest of your switches, and they will fall in line. So it's very, very important that whoever your root bridge is has this information set correctly, and if your root bridge changes, these numbers may change. So some different versions of spanning tree that we'll talk about. The original common spanning tree is what they call it, 802.1d. And then we also have a version of PVST Plus, which is Cisco proprietary version of common spanning tree. Then we also have rapid spanning tree, which is 802.1w. Then Cisco made a rapid spanning tree, rapid Per-VLAN spanning tree plus, which is a Cisco proprietary version of it that integrates our VLANs into it, where we have Per-VLAN. And then we had what is really a revolution when it comes to spanning tree, and that is multiple spanning tree. So multiple spanning tree is a IEEE standard, and MST is Cisco's implementation of multiple spanning tree. So this really bridges the gap that we had between our traditional spanning tree and our Per-VLAN spanning tree, where now we have instances of spanning tree, and we can assign by default that to all of our VLANs, or we can assign multiple VLANs to one instance of spanning tree. Because having Per-VLAN spanning tree is just fine until you have 4,000 VLANs. When you have 4,000 VLANs, running 4,000 instances of spanning tree does not scale well. So we're going to use multiple spanning tree, and maybe we can have 4 instances, one per each 1,000 VLANs, and that way we can really utilize our hardware without having to compromise on our links. So rapid spanning tree removes some steps to make spanning tree faster. 15 seconds for a port to activate is not acceptable in today's environment. Our users expect things much, much quicker than 15 seconds. So they removed the disabled, blocking, and listening phases and replaced them with a discarding phase. This allowed very, very great improvements in the convergence time. And convergence, if you're not familiar with that term, is really just our whole network acting as one. It's all it's been communicated, everything's set up, everything's up and going. And so the convergence time is the time really spanning tree gets to where everything is working as it should. Now our port fast option is going to be, now these are really options we have for our ports. The port fast is going to skip listening and learning states. It improves time for a link to come up. So if you know that a link is probably not going to get plugged into a switch, you can set this port fast. The only downside is if it gets plugged into a switch, then you may have 15 seconds or so of a loop, and you may cause temporary issues and outages very, very temporarily. BPDU guard will shut down a port if a BPDU is received on that interface. It's very recommended to use BPDU guard anytime you use port fast, because that will shut down the interface if for some reason it gets plugged into a switch and you didn't expect it. Now, BPDU filter should only be used in very specific situations. BPDU filter will drop incoming BPDUs on that interface, but will not disable the interface. So if there is a switch on that interface, it won't disable the port, but it just will ignore any spanning tree information coming from that port. This may be useful if you're working with another organization, you're connecting, but otherwise is usually a bad sign. You usually don't want to set that up. So some alternatives to spanning tree. If you really, really hate spanning tree and you want to do something different, of course, you can implement a layer 3 campus design. The downside there is a layer 3 campus design is much more complicated, and I find that people who have a limited understanding of networking really struggle with layer 3 design. So if you have any entry-level IT people, or entry-level networking people even, you could have issues with them understanding how that networking works. I know that at my current employer, I have issues with explaining how our networking works to other IT people in more desktop type roles. And so when you have issues dealing with explaining a very simple concept, introducing a layer 3 campus design may be very complex and difficult for them to do some basic troubleshooting with, which would then in turn lead more work on the networking team than would otherwise be. So it really depends on your situation, how large of a team, how skilled your team is, and really just kind of it really takes knowing the organization to know if you should go for a layer 3 campus design. Enterprises are more and more using designs that resemble data centers, layer 3 design. Of course, it's more complicated. It's more efficient and predictable for network engineers. However, like I said, for a lot of entry-level people, for a lot of desktop technicians, they don't understand it, and so it may not be a great alternative for you. However, I do love the idea of a layer 3 campus design personally. So here are some terms you should be familiar with after this. You should be familiar with 802.1d and W. These are the original standards, the spanning tree standard and rapid spanning tree standard. What a broadcast form is, a root bridge, root port, right? Those go together. Designated ports, alternative or blocked ports, listening, learning, root bridge IDs, root IDs, BPDUs, very, very important here, especially when you get to CCNP level stuff. Just kind of go through these and think about them. Do you know what multiple spanning tree is? Do you remember what that is? If not, go back, review, and I think that's it. So I will see you guys in the next video.